And what that means is if all cells come from pre-existing cells, there must be some method by which cells can divide. Now, there are two methods of doing this. One is used by prokaryotic cells, and one method is used by eukaryotic cells. Prokaryotes, just left out an entire letter. Prokaryotes are going to use what we call binary fission. So they just, divide it in half. It's a very simple thing. It's because they're very simple cells, not a big deal. That's not the one that we're going to focus on. So that will not be the one that we focus on. Instead, we're going to focus on how eukaryotic cells divide. The life cycle of a human. That's one you're familiar with. Easy peasy. How does it start? Okay. Step one. And then, shortly after conception, that looks kind of like a little alien all curled up, right? Okay. Goes from little alien to larger alien to larger alien to alien on the outside. My alien on the outside only has one eye. Okay. Listen, don't judge it. Its eyes are really close together, okay? It's going to get picked on a lot. After it goes to little alien on the outside, what is it? What? All right, toddler. Gotta make my... Earlier I was criticized that my toddler was smaller than my little alien on the outside. Everybody's a critic. So let's get some scale here. All right. And then from toddler, slightly larger toddler. Oh, wow, its head got bigger. Poor kid. Not only is its head huge, its eyes are also super close together. And then what? Eventually we reach full size. And we stay full size for a little while, right? Doing whatever it is you're going to do when you stay full sized. And then, strangely enough, you go from full size to less than full size. Right? Old people get smaller when they get old. It's just what happens. They senesce. It's the polite way to say you got old. Senesced. So this whole thing is a natural cycle, right? It's a cycle of growth and development. And then a part of the cycle that I would call stasis. Just stasis sound like it means. Stasis.
Sounds like homeostasis and maintaining the same.
It's exactly what happens here. Status quo, right? Stasis. All just kind of keeps doing its thing. And then it ages. Now, for the average human, it's kind of hard to say average human. For the average human in the United States, oh wait, we can't say that either. For the average female in the United States, that's probably about, 82 now? Average male in the United States, I think it's still somewhere around 76. Sorry, guys. But that's how long this whole process takes. Your cells are going to do something very similar. They have an area of growth and development. They have an area of stasis, where they just kind of go about life processes. And then they have an area in which they get old. And sometimes getting old means they just kind of be, and then sometimes it means something that, actually, if you translate it into human equivalent, is truly horrendous. It is a scheduled cell death. Sort of like euthanasia for cells. It gets dismantled for its parts and reused. We don't do that to people. Just so we're all clear. Right? Some of you are like, How many of you are considering dismantling an old person and using them for parts? I saw you think about it.
Don't we kind of do that if it's like an organ donor?
Well, you don't dismantle them per se. You harvest the organs, but like you don't like recycle the rest of them.
It's not like,
That's what they call it. They call it harvesting. I don't know. For a cell, it looks more like this. The cycle is going to begin at the beginning. Logical place to start. There's a period of growth. There's a period in which one prepares for division. You could call this that like adolescent area of puberty in our previous slide. Where one then, in the second area of growth, you had like growth from infancy to pre-adolescence. You have adolescence, where puberty begins. And then you have, ideally, what is young adulthood, where one then begins to establish the necessary money, career, etc., to be able to have a family. And then division occurs. We have a new cell. I dislike the fact, though, that we're calling this the cell cycle when this diagram makes it a straight line. Where I come from, cycle implies circle. Agreed? It's a circle. Don't judge. Shh. No, it's the division of my circle in the middle. Like if I were the guy at the pizza place who had to cut that pizza into pieces, I would get fired. Right? Yeah, those are not equal pieces of pizza. This is the exact same thing we saw in the previous slide. I just took it and turned my circle. So it took the arrow by its tail, grabbed it, and made a circle out of it. So I can label it with the same parts. Ah, see? Just made it a circle. So I'll let you sketch that for the moment, and then we'll fill it out. I've written the names of all of these sections over here, where we have G1 stands for gap 1, S stands for synthesis, and G2 stands for gap 2. Consider the beginning of this right here, at the birth of a new cell. When a new cell has been created, it goes through gap 1 first. That's the first area of cell growth. It's how we went from conception on the human slide to pre-adolescence. So all of that occurs in this stretch. The cell is going to get bigger. The cell is going to produce more organelles if it should happen to need them. In some cells, they're going to just simply go about their life processes. So that process where in gap 1, it's cell growth and differentiation. Differentiation is just the biological term for a cell getting its assignment and then performing the assignment. So what I mean is a liver cell is told that it's a liver cell. And then it goes about being a liver cell, doing what liver cells do. A brain cell is told that it's a brain cell, and then it goes about being a brain cell. Your skin cells get a message, tells it what to do, and then it goes about doing that. The process of receiving the specific tissue that you belong to is called differentiation. So gap 1 is growth and differentiation. Now some cells don't actually have to divide again. I'll give you some examples of cells that don't divide again. Oh, when you reach full size, you are yet to be full-size people. I am a full-size people. Yep. Differentiation. Different. I-A-T-I-O-N. So I'm a full-size people. I've been a full-size people since my brain stopped developing somewhere around the age of 25. And that means that all of my internal organs needed to stop growing. Like my liver and my kidneys, when I reached full size, were full size. And if they continued to get bigger, while the rest of me did not, where are they going to go? And suddenly you're like, good point. Yeah, it's just gonna get bigger and bigger and bigger until I like hemorrhage, right? Until it pops out. So somebody earlier first hour was like, is that possible for an organ to pop out? Well, yeah, what do you think a hernia is? Right? Your intestines popping out. Yeah. Nobody told you guys that before? Here's how this thing works. Your whole midsection is a cage of muscle. And its job is to keep everything on the inside smashed in there. And if something pops out of that cage of muscle, it punctures a hole in the cage of muscle and then it sticks out. And so when you get a hernia, it's because your intestine pops through and sticks out. So they have to go in and stick it back in and then stitch it up. How many of you want to be doctors now? Those of you who don't want to be doctors, don't worry. By the look on your face, I can tell you. Now any of you know somebody who had hernia surgery probably feel a lot worse for them now, don't you? Those things, it doesn't seem like that big of a deal. You're like, oh, okay, if it popped out, you could stick it back in. Okay, fine. Here's another one, my brain. My skull reached full size, and hopefully you guys recognize that thing that holds your brain is hard. Yes? Not getting any bigger? If my brain were to continue to grow, where would it go? Can it go anywhere? So all it does is it would increase pressure on the inside of my skull. It would be a wicked headache. Those of you who are familiar with the idea that your brain, when it swells or when you get a concussion, it hits the side of your skull, and then your brain swells and you get that massive headache and all that. If you sustain that kind of brain injury and the swelling doesn't stop, some of you may have heard of a shunt. And they have to put a shunt in to relieve pressure. It drains off the fluid so your brain has room to expand. So if any of those differentiated tissues divided after they needed to divide, it would be horrible. It would mean certain death for the organism that it happened to. So there has to be a way that things can exit the cell cycle and just exist. And they do. There are certain cells, the ones who don't need to divide anymore, who will exit the cell cycle this way and go into what we call G0. They live, they're alive, they're not scheduled to die. They're just there being. And how long they're in G0 depends on what tissue it is. Yep.
Do they like go through G1 or do they not?
After growth, they're gonna just branch off on the side. Consider it like a rest stop. Like you get off the freeway for as long as you need to and just hang out there. That's what they do.
So they just exist.
Mm-hmm.
And they go like back and
Only if that particular body part sustains an injury. And they have to make a new cell to repair injury.
where do they go? Do they just like transfer to?
They just be the tissue that they're meant to be. So for example, my brain, those cells entered G0 sometime around when I was 25, and they have been there existing in my skull in G0, just being brain. The only reason they would exit G0 is if I were to get concussed. Anything near the area of concussion would exit G0, repair the tissue, and then go back out to G0 after the repair is done.
This is where they go like.
Mhm.
Are there other cells that just go to G0 after the division?
Any cell that belongs to a tissue that doesn't divide or doesn't get bigger. So after you reach adult size, things that just aren't going to divide, liver, kidney, your intestines have to keep dividing because you're constantly digesting surface, right? Like it just continues to wear away. Your eyes wouldn't necessarily need to, certainly not the vitreous. Brain wouldn't need to, spinal cord wouldn't need to. So anything that just exists as is. Your bones always will, so they'll always continue to divide. But the rate at which they do that depends on the kind of tissue that they belong to. So, like, my brain, God willing, I'm going to rock these same brain cells from when I hit the age of 25 until I hit, like, 99, like my grandma. My bone, if I were to break a bone, it's going to have to repair itself and make new bone tissue. So it all depends. My skin, well, we all leave a little pile of skin cells everywhere we go. So you're sitting in a pile of somebody else's skin cells. Actually, that's not true. Like the 5 people who occupied that chair before you today, you're sitting in 5 people's piles of skin cells. Some of you look very shifty and uncomfortable. Better hope they were someone you trust. So that has to be really quick. Your skin cells are going to go through that process in a matter of like a week because they always have to replace themselves when you slough them off. So this depends on what tissue you're a part of.
Eventually, does everything stop growing at some point?
Yes. So typically what would happen, everything's going to stop growing because your cells are going to get to the point that they're so old that they just recognize that they're not going to divide anymore. It's based on the length of their chromosomes. The shorter the chromosomes get, the less likely it is they'll divide. That's why old people, when they get hurt, take longer to heal because their body's not doing this as fast as they did when they were spring chickens. So, and biologically it makes sense.
Do the cells still age when they're in G0?
Mm-hmm. So they get less efficient at what they do. Don't tell any of your loved old ones that, by the way. It's a really good way to make them angry. Like, oh, your really old cells are slow. Sorry. That would not be amused. Like we said, though, G0, if injury is sustained, it can get back on. That's why I like the idea of it being a rest stop. You get off the freeway for as long as you need to. You can get back on. Well, I hope you get back on or you'd still be at that rest stop. Be awkward. From there, after growth is completed, we enter what we call synthesis. Synthesis is when DNA replicates. So that's when DNA replicates. Since this whole thing is preparing for a cell to divide, that means that there has to be 2 copies of all of the DNA. It's often a misunderstanding amongst students how much DNA there is in every cell they have. Every single cell that you have has every single base that you have. So you have 6 billion nucleotides in every single cell. All of them. Not just the DNA that cell needs. It has all of your DNA in every single cell. So that means before it's going to divide, it needs to make a copy of all of your DNA. That happens here. After that process, we enter gap 2. Yep.
I've heard of, like, they've done these experiments where they stuck 2 twins together in one room. And twins don't share the same DNA, so would they have, like, goal sets?
So you're talking about identical twins?
Or something like that, I guess?
So I don't know that I understand said question. Can you rephrase it?
I don't know.
Think on it and ask me again.
Alright.
And I'll find the best way to answer it. So every cell you have, right? Well, not every cell. What cells don't have all of your DNA? They are cells you had better not yet be considering using.
Your reproductive cells?
Yeah, your eggs and sperm, they only have half. If not, you'd have a very strange baby. That would be bizarre. So, every cell you have is going to have all of those. It has to be copied there. And I think I compared GAP2 to when you get a college degree and a job and all that, like you prepare to start a family. So this is when the cell is going to start accumulating all of the chemicals and all of the things that it needs to divide in half. It's got to prepare for it. It needs to double the amount of organelles it has. It has to work on how much cytoplasm it has in GAP2. Once it leaves GAP2, it's finally ready to start division. That process of GAP1 synthesis and GAP2 is called interphase. And that's what cells are doing when they're not dividing. If you were to look at a slide, a microscope slide, of cells, the vast majority of the cells that you look at are going to be in interphase. They are not going to be dividing. They're just going to be doing their thing. When they go to divide, that's when they begin the process of mitosis. I want to be very, very specific about what mitosis is, though. Mitosis is the division of the nuclear contents, the stuff within the nucleus. So that's when the nucleus divides. When the cell itself divides is a separate process that I kind of drew in right here as a big white wedge. It occurs at the very end of mitosis, and we call it cytokinesis. Before we begin to talk about anything that occurs in M, we need to remember all these parts, because all these parts are really important players of that particular game. Everybody has a role. So we have the nucleolus where ribosomes are made, right? We have chromatin that contains all of the genetic material of that cell. Centrioles that when we learned organelles we said were just, actually we vaguely glossed over them and I said, you'll worry about them when we get to cell division. Well, here we are. And you have a cell membrane. Only other thing that's going to become important are going to be small fibers that are going to form from the centrioles that we call spindle fibers. They're going to form from the centrioles, but there won't be a nucleus at the time. So just know that spindle fibers form from the centrioles. That stuff. Double helix composed of nucleotides. And to fit all of your DNA into a cell, there has to be some pretty creative packaging. So the first thing that's going to happen is it's going to wrap around a small protein ball called a histone. So when DNA wraps around histones, then you get your chromatin. That's all that chromatin is. Multiple histones are going to form into a little flower shape, and that makes a nucleosome. And those nucleosomes are going to continue to wrap around themselves until they make a chromosome. So chromosomes are just convenient little packages of DNA meant to make sure that all of the DNA is neatly and tidily all packed up. It's a group of histones. They form like a flower shape. We believe it's actually 8 histones. So you end up with something in your chromosomes that look like a giant X. Each leg of that giant X is called a sister chromatid. So each leg of the giant X is called a sister chromatid. And here's what most people misunderstand about that. Sister chromatids are identical. So this side here, that I'm going to draw diagonal slashes through, contains exactly the same DNA in the same order, in the same locations, as the one that I'm covering with stars. This thing is the centromere. So if we look back at our diagram, interphase, mitosis. Now, you told me that cells just keep dividing, but I can guarantee you that if cells kept dividing with no checks or checkpoints, that would be a very, very bad thing. Cells that divide without any kind of check on their dividing become cancer. Because they're tumors, right? Because that's all a tumor is a cell that just divides and divides and divides and divides. And since it divides, every cell that it makes divides. So you go from 1 sick cell to 2, from 2 to 4, 4 to 8, 8 to 16, and it grows exponentially, right? That's a tumor. So there has to be a way to prevent that from happening. Your body is brilliant enough, any eukaryote is brilliant enough that it has some methods already built in. Those methods are what we call checkpoints. They are the mitosis checkpoints. G1 checks to make sure that it's a cell that is actually allowed to divide. Like if it's like, hey, you're a brain cell, you're not supposed to be dividing, then it won't divide. S phase checks to see if the DNA is healthy. If it's good DNA, if it's healthy DNA, then the DNA is allowed to replicate. During G2, it double checks to make sure that the replication that occurred in the previous step was accurate, that there were no mistakes made. And then M is going to check something else the mitosis, the metaphase checkpoint, is going to check something else very important, that everything is aligned where it's supposed to be for cell division.
What was S again?
S is to make sure that everything, that the DNA is good, like there's nothing wrong with it. If there is something wrong, either it gets fixed, that's one option, you can fix it, or the cell is scheduled to die. That's what apoptosis is.